Recall Bernoulli's equation from our previous discussion. If we consider a fluid that doesn't change its elevation, then y1 equals y2, and Bernoulli's equation reduces to the following. This tells us the quantity p plus 1/2 rho v squared remains constant. Therefore, if v increases, p decreases and vice versa. In other words, the pressure in a fluid is lower when the speed of the fluid increases. There are many common situations and applications where this occurs. A fluid moving at different speeds on different sides of a single object will produce pressure differences around the object, and thus forces on the object. In the rest of this section, we will use Bernoulli's equation to qualitatively explain several common examples showing the effect of a moving fluid. As our first example, consider the impact of fluid flow in household plumbing. The figure shows a large drain pipe connected to the drains of a clothes washer and a sink. When water from the clothes washer rushes through the sewer pipe, the high-speed flow causes the pressure at point A to drop. The pressure at point B in the sink remains at the higher atmospheric pressure, and it pushes the water out of the sink trap into the sewer pipe, thereby emptying the trap. This is not a good situation, since an empty trap can allow sewer gas to enter the house through the sink. A correctly designed system utilizes a vent pipe that keeps both points A and B at atmospheric pressure, even when water from the clothes washer rushes through the sewer line. Thus, the purpose of the vent is to prevent the water-filled trap from being emptied, not to provide an escape for sewer gas. The following video demonstrates this effect. We have placed a straw vertically in a dark liquid. We then blow air out of a second straw across the top of the first one. This would represent the water flowing out of the clothes washer. This fast-moving air lowers the pressure above the vertical straw in accordance with Bernoulli's principle, and the higher atmospheric pressure pushes the liquid up the straw. If we blow hard enough, we can actually push the liquid all the way up and out of the straw. Our second example is to look at the physics of an airplane wing. There are 4 forces that act on an airplane in flight: its weight, the thrust from its engine, drag from the air resistance, and a lift force. It's the wings of the airplane that produce the lift. As the figure shows, air rushes both above and below the wing as it moves through the air. Thus, the pressure both above and below the wing is reduced relative to atmospheric pressure. However, because of the wing's shape, the air across the top of the wing moves faster relative to the air beneath it. This creates a lower pressure on the top of the wing, and the higher pressure beneath the wing pushes it upward, creating the lift. As this simple demonstration video of an airplane wing shows, blowing down across the top of a piece of paper actually causes it to lift upward. The faster moving air across the top of the paper creates a lower pressure, and the higher pressure beneath the paper pushes it upward. Another common example of the impact of fluid flow is the curveball, which is one of the most effective pitches against hitters in baseball. The figure shows the top view of a baseball thrown without spin. The air moves around the ball equally on all sides, and the ball does not curve. However, if the ball is spinning, say counterclockwise as viewed from above, the air near the surface of the ball is dragged along with it. This slightly increases the speed of the air near the ball on the side that is spinning in the same direction as the air rushing by. This lowers the air pressure on this side of the ball. The higher pressure on the other side pushes the ball in that direction, thereby causing it to curve. In this video, an instructor uses a sidearm throwing motion to flick a styrofoam ball off of the end of a V-shaped board. This causes the ball to spin quickly upon release. The difference in pressure on the two sides of the ball pushes it in a curved path. In our final section of Chapter 11, we will see how to take into account the viscosity of a fluid.